already have introduced myself. So my another work is on TiO2 decorated MoS2 nanocomposite for CO2 sensing at room temperature. So it is well known that CO2 is an important major greenhouse occurring gas, and it is crucial for life, but it has some harmful impact on human and environment if it is in excessive concentration. So it is observed that over the past 200 years, the normal concentration level of CO2 rises up to 50% in the environment. So it is important to monitor the CO2 level in environment to study the greenhouse effect, improve the indoor air quality, increase the crop production, and it is also useful in biomedical application. CO2 monitoring is also very important part in food packaging, as CO2 generated by microbial activity is a key food spoiler. So as we can see in the graph here, this graph, uh, the concentration of CO2 rises from 320 ppm to 420 ppm from 1960 to 2020. So this is all because of human activity. And in market, there are two type of CO2 sensors are available. One is NDIR type of CO2 sensor, other is metal oxide based electrochemical sensors. And here we will discuss about electrochemical sensors because uh, electrochemical sensors have wide application because of compactness. It is useful in space research, fire detection, emission monitoring, aerospace application, and other biological application. So we can see in the animation graph that semiconductor type of electrochemical sensor generally use metal oxides. Uh, 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 the structure is like that. In electrode, we have deposited some sensing layer, generally metal oxide, and we have a heater underneath the substrate to elevate the temperature for the sensing purpose. So when analyte come in the vicinity of the sensing layer, there is a carrier charges transfer between the gases and the semiconducting layer, which changes the resistivity of that sensing material and which is calibrated according to the concentration of the gas present in the vicinity of that environment. So in this way, our electrochemical type of semiconducting sensor behaves. So some state of art work is that earlier developed sensors generally uses temperature beyond 150 degrees Celsius, and those are based on the metal oxide or their nanocomposite like copper oxide, ZNO, TiO2, or some other type of metal oxide. As we can see that they suffer from selectivity issue at room temperature, even at higher temperature. In figure first, we can see that there is a TiS2 nanodisk based sensor at room temperature, but selectivity is fine, but it is limited to NH3COCH4, and most of the sensor do not show selectivity for CO2 sensing, and because CO2 is also a inner type of gas. And at room temperature, there is challenges with response time, and recovery time. In figures B, we can see that there is very low response in 0.0018 for RGO or RGO PI based nanocomposite. So these are the challenges we are facing in CO2 sensing. And figure C, we can see that the selectivity improves with temperature, but not quite good. Sorry, response is improving, but not quite good. So these are the challenges faced by the CO2 sensing development. So here we have used MoS2 as a sensing material because of its superior sensing capability at room temperature. It have high surface to volume ratio, and its band gap can be tuned. Its absorption coefficient is high, and it can be easily functionalized with polymer or metal oxide or some other functional groups. So we here utilized MoS2 to develop a room temperature sensing, but it also lacks selectivity, and we can use metal oxide to improve its selectivity as well as response and recovery time. So metal oxide can be used to improve its response and recovery time as well as selectivity. We moved with the objective to develop room temperature CO2 sensors based on MoS2 and TiO2, which have high response, selectivity at room temperature, short response time, and short recovery time. We have developed sensor using screen printing. So first we developed electrode on a silicon substrate using screen frame and which having mesh. So we have print, this is the original picture of mesh and this is two electrode system. So we used carbon paste, carbon graphene paste and squeezed on the substrate so that these pattern are printed on the silicon wafer. So and these are the original picture of the electrode and it have nearly gap of 500 micron. So after fabricating electrode, we have prepared MoS2 using hydrothermal technique. We use thoria and that hexaammonia heptamolybdate tetrahydrate, and we have kept it in oven for 220 degrees Celsius at 2 hours to grow the MoS2 nano flower and then filter it out using washing several times. These are the this is the same image of prepared MoS2 nano flower. We can see it at 200 nanometer scale. Then we have stirred and sonicated it for some time and then drop casted on the prepared electrode as we have seen on the previous slide. Then we have spin coated on this electrode, and this is the final developed device. And this device we have characterized in the sensing chamber. So here is the material characterization result. We have performed EDS analysis to check the prepared MoS2 and TiO2 concentration. And actually we prepared for 15:1 of MO to Ti weight ratio and it is found nearly same after the EDS analysis. And we performed XRD analysis to confirm the presence of MoS2 and FeO2 3 in the developed sensor. And we also measured the thickness of the sensing layer and it is found around 2.2 micron using AFM technique. These are the sensing results and we can see the change in the resistance when the concentration rises from 500 ppm to 5000 ppm for CO2 and the baseline is around 4.46 mega ohm. On the second image, we can see the response and recovery time. Response time changes from 88 seconds to 470 seconds for the CO2 for 500 ppm to 5000 ppm. Similarly, recovery time is very fast from 27 seconds to 170 seconds. And at 150 degrees, at 500 ppm, we can see that response is nearly 1%. Here in the graph also we can see we have calculated the sensitivity using this linear graph and found that sensitivity is quite low, but it can be used to detect the CO2. It is around 0.0032% per ppm. RMS noise is determined around 0.45 ppm and similarly theoretical limit of detection is 423, which is lower than that our environmental CO2 level as we have discussed in the introduction section. So we have also studied the reliability and stability of the sensor in humid environment, variation with temperature, repeatability and stability of the device. And we found that our sensing performance figure A, we can see that there are sensing response of TiO2, MoS2, and at various decoration ratio of TiO2. And we found that that our sensor is optimized for the 12 molar percent ratio of TiO2 over MoS2. Similarly, in the second graph, the variation with humidity is also studied up to 40%, and we can see that at 40% also, it is showing significant response, nearly 1.5% of the response. And figure C show the repeatability of the graph, repeatability of the sensor, and repeatability is quite good, nearly 0.092% of variation. And we have developed multiple devices, 4 devices nearly, and the variation in device to device variability is around 6.6%. So we have compared our device with some previous literature. these we found that our sensor is working fine with a wide range of detection, nearly 500 to 5000 ppm, and response and recovery time is also low as compared to previous works, and most of the previous work are around more than 150 degrees Celsius of the temperature, and those which are at room temperature showing low response as well as high response and recovery time. So the concluding point that our developed MoS2's TiO2 nanocomposite shows high selectivity for CO2 with respect to SO2, CO, and NO2 gases, even at elevated temperature. The sensing response lie between 1 to 9% for 500 to 5000 ppm of CO2 with limit of detection is 423 ppm. Fabricated device so response and recovery time of 88 second to 27 second for 5 ppm of CO2, and sensors have shown good sensitivity and reproducibility with 6.6% of variability, and the sensor is fully printed on glass electrode, sorry, glass substrate. So thank you.